prove using vectors that the internal bisectors of the angles of a triangle are concurrent. Okay, so let's try to understand the problem graphically first. So here we have the triangle ABC. AD, BE and CF are the internal bisectors of the angle A, B and C respectively of the triangle. So our goal will be to verify using vector that these three internal bisectors, the AD, BE and CF, all meet at the same point. So let's call this as the point I. That means these three lines are concurrent. Okay. So first what we'll do, we'll consider a point O, which is going to be the origin of some coordinate system. Now with respect to this origin, we can define the position vector of the three vertices of the triangle. So let A vector correspond to the vertex A, B vector correspond to B and C vector correspond to the vector C. That is, let OA vector, let this be A vector, OB vector, let this be equals to B vector and OC vector equals to C vector. Okay, so what we'll do, we'll first try to find out the ratio in which I divide the internal bisector of angle A, that is AD. To do that, what we'll do, we'll consider the side opposite to the vertex A as A. It's just a scalar number A. Then the side opposite to angle B, let's consider it to be equivalent to B. And the side opposite to angle C, we're going to consider it to be C. So here, let's note it down. Also, let BC to be equals to A, CA to be equals to B, and AB equivalent to the C. That means the length of AB to be C. Since AD bisects the angle BAC internally, so this would mean internally, so this would simply mean that if we take BD over DC, this will be equals to the ratio of AB to that of AC. Fine. Now we have already defined that AB corresponds to C and AC corresponds to B. So here we have BD to the ratio BD to that of DC equals C over B. That means we can say that D divides BC in the ratio C is to B. Okay, so let's use this fact. That simply means that D divides BC in the ratio C is to B internally, which means that now we can apply here the internal section formula. So this means that the position vector of point D will be equals to C times the vector C. We have C times C vector added to this B multiplied to the position vector of vertex B. So we have B times B vector whole divided by C plus B. C plus B. We're going to label this as number 1. We're going to keep this aside for the time being. Also, from this figure, we can say that BE is the internal bisector of angle ABC. If B is the internal bisector of angle ABC, we can also consider BI to be the internal bisector of ABC. It means exactly the same thing. This is also the internal bisector of ABC, which means that now if we take the ratio of AI to that of ID, then this is going to be equals to, we have BA to that of BD. Fine. Now, we know BA it's already defined as C, but we have to now find BD. So we need to find BD. BD is not actually C here. This is a ratio in which D is dividing BC into BC. So here, in order to find out the length of BD, so here we're going to use a little bit of geometry. Now since the ratio of CD to that of BD, so this is B is to C. So what we can do, we can add 1 to both sides to get CD plus BD divided by BD equals to B plus C divided by C. So all we have done is added 1 to both sides. Now what is CD added to BD? CD added to BD, that's nothing but the length A. So we have A over BD. So this will be equals to B plus C over C. So arranging for BD. So BD comes out to be AC divided by B plus C. That means here we can substitute in place of BD with AC over B plus C. So here C and C gets factored out, and this gives us the ratio AI to that of ID as now we get B plus C to that of A. So going back to our diagram, so here we have obtained that AI to that of ID is B plus C over B plus C, and ID is going to be A. So in other words, we can say that this implies that I divides AD in the ratio B plus C is to A internally. Fine. So if it's dividing it into ratio, now what we can do, we can apply the internal section formula. So here, this means that the position vector of OI vector, this is simply going to be, so we'll take B plus C, and this is going to get multiplied with the position vector of point D. So that means OD vector added to, next we have A. So A is going to get multiplied with the position vector of the vertex A. That means A vector. We have A times A vector whole divided by, we're going to divide with B plus C added to A. So OD vector, we have already defined the position vector of point D. So OD vector is CC vector plus BB vector divided by C plus B. So let's use this. So this is going to be B plus C multiplied to C times C vector added to B times B vector divided by C plus B added to A times A vector whole divided by A plus B plus C. So here we can factor out B plus C and C plus B. These are two scalars. So this gives us OI vector. This will be equals to A times A vector plus B times B vector plus C times C vector whole divided by A plus B plus C. Fine. So here we have found out the position vector of the point I when we consider AD. Similarly, if we consider B, the integral bisector of angle ABC, we can still find out, we can still see that the position vector of I comes out to be A vector plus BB vector plus C vector divided by A plus B plus C. And also, if we consider the angle bisector of angle C, that is CF, that's also going to give us the same result. So this means that so we have success that I'll be leaving as an exercise for you to try out. So hence we can say that hence the internal bisectors of a triangle are concurrent. That means they meet at the same point. So this proves a problem.